Okay, welcome back. Brief housekeeping before we start. Okay, so the deadline for second assignment has just passed, and if you go to Gradebook on your NTU Learn, you can check your grades. Okay. Now assignment one is still being graded. The TA has been a little sick, so it's been slow in grading, but eventually you'll see the assignment one grades. The solution to the assignment one will be posted probably sometime later tomorrow. Just waiting for a couple things to get checked out. And hopefully you have already tried to see your practice quiz grade as you try to do your assignment two, right? And assignment two grade here is literally just an average of your practice quiz, right? So I just made a function that does that. Okay, so assignment two grade should be posted for you. Assignment one grade, some of you have it posted, some of you are still waiting. That's normal. And then assignment three has been released last night, and then it'll be due just before the quiz or next week. So that's how it goes. The labs, I think most of you have been signed. Okay, I think they might be still signing the lab. So, if you haven't heard back, or if you don't see lab sections in your schedule yet, okay, maybe it's a good time to get in touch with the academic office and see when they'll finalize. Okay, it's not something I can arbitrarily create and put you in. Right, it has to be done through the academic office. So we have to kind of wait for them to finalize. Okay, so that is the NT Learn stuff, right? Okay, quiz one next week. All right, that is the 10% of your grade. All right. So it amounts as much as the entire percentage of the assignments put together. But I think you have a pretty good idea what it's going to look like already. Okay, your practice quiz 3 and 4 are the previous year quizzes, right? So you can kind of expect what it's going to be like. Okay, especially for the first quiz, I try to make some buffer so you don't get so nervous, all right? So at least five or more, right? Will be from the questions you have already seen in your practice quizzes. Okay, so hopefully, but like always there are students who miss those questions. I think it's just a mistake, but. Okay, so hopefully, the minimum score anyone gets will be 5 out of 15. But we'll see. All right, so 15 problems, 30 minutes, so 2 minutes each. So obviously, I'm not expecting you to do a lot of calculation in this problem, right? So if you look at a problem and you think that, I need to do a lot of calculation, or thinking that you're probably approaching it the wrong way, right? So these are it's a little bit like a college entrance exam test. So it's kind of just poking at conceptual things, whether you understand it or not, or you spend the time with assignments and tutorials, etc. Okay, so. I think I probably, so 5 of them you already seen it, so it's going to be very similar or identical, actually. Probably the other 5 or more will be, a lot on something that you can do it if you did attend the lectures and the quizzes, did tutorials and things like that. And, maybe there are 3 or 4 problems that are slightly more challenging while not requiring a lot of time to do, right? So those will be the kind of a mix that you can expect to see in the quiz, right? Now, that being all said, at the end of the day, statistically speaking, I've been seeing this, I've been course coordinating for this course for 2-3 semesters. Most of the time, your final grade is really determined by your final exam, okay? So just because you don't do well in the quiz doesn't mean you're going to get a bad grade, but the other way is also true. Just because you did well in the quiz, you're not going to get a good grade, right? So really, ultimately, we're kind of working towards preparing you for the kind of final exam at the end of the day, right? So that should be the kind of mindset you have. We have a fairly big class. We don't have that great of attendance here, but actually there are, we have about 210, 220-ish people registered. 60 of them are part-time, so I think for the full-time, which are you, there'll be about 160 of us. Hopefully most of you show up. It'll be too crowded in here, okay? So what we're gonna do next week is we'll do a half an hour of a lecture, and then we'll just pack and we'll go to exam hall C, okay? It's more spacious, AC, and etc. Now I can promise about the accessibility to the power adapters, all right? So make sure your tablets, PC, whatever you're gonna use are fully charged, operational. Once again, if you have issues with the batteries or laptops or whatever, okay, the department loans these laptops, okay? So you can just go to the academic office and tell them, hey, I need this for the quiz, and they will give you the laptop for you to use to take the quiz, okay? So those are the options there, okay? And so after the exam in exam hall C, all right, hopefully, we'll end around just before 2 or 1:50, because it probably takes like 10 minutes to walk over there and settle, all right? So that'll be like 1:10, we start the quiz, so 1:40, we should be wrapping up the quiz, but, put a buffer, 10 minutes, so should be done by like 1:50 as usual, all right? So that's the timeline, okay? And then there will be, I think, about 6 TAs present, including myself as a proctor, so don't be alarmed if you see some strangers walking around looking at you when they're proctors, okay? And the closing remark on this is that, you see a lot of these, in the example and tutorials, you get exposed to a lot of these kind of lengthy problems, right? You kind of solve it with mesh or nodal analysis, and you have to solve them out. But if you go to like job interview, right? Or if you actually face certain problems in practice, right? You need to make certain decisions fairly quickly, okay? And in the same token, if you go to interview, they're not going to give you a circuit and ask you to do the mesh analysis, right? It's just not enough time, right? Interviews will be like 20 minutes, and then they're just trying to gauge whether you know your stuff or not. All right, so they'll ask questions similar to what you see in the quiz here, all right? So take this as not only just a quiz for the class, but kind of consider that as preparation for interviews that you will eventually have to take to get a job or an internship and whatnot, right? All right, so that's the housekeeping. Any questions? Well, it covers everything that we covered until this week, all right? So first 3 weeks. Okay. All right, if you have any questions or if you want to meet up one-to-one to ask questions, just let me know, all right? We can set up a time. I'll probably provide some recording of me going over the solutions to assignments and other things probably on Friday, all right? So you'll be able to, I send out a time. I'm trying to sort out the lecture location and stuff. You can attend it in person or you can just watch it, all right? It'll be recorded. But the solution will also be posted at NTU Learn, so if you just prefer to look at it yourself, you could. Okay, brief recap. All right, so we start with the Ohm's law, V equal to IR, and then we briefly talked about how there are always quantities that are opposite of something. And the opposite of the resistance, opposite of being resistant to flow of current is conducive to the flow of current, which is the conductance, right? So it can be presented in either way when you describe a circuit that has resistor characteristics or resistances. Okay, and then we looked at KCL, KVL. Okay, so you also signed the assignment. You need to describe it, what it is. I think everyone can do it pretty well. The only part that people make mistake, again, is assign mistakes, right? So in the last couple lectures, we had some simple examples for you to kind of do a mental exercise, not to make the sign mistakes, or at least providing you a way of checking whether you made a sign mistake or not. So do make sure that that makes sense to you, okay? Because in the quiz, I'll probably throw you something, doesn't require calculation, but based on the arrow directions, you need to get the signs right or something. Just like you signed the practice quiz 3 and 4, right? So make sure you don't make sign mistakes, all right? And then the other thing we talked about is the linear system allows you superposition, okay? So I think this is one of the things that people don't think so much about, but it's basically, okay. So I'm just showing you in multiple ways. Like last time we saw some way, this time we're seeing some way. If you consider a function, f, okay? If it's a linear system, what you can do is you can separate them out like this, okay? So what I mean by that is, so when we say v equal to IR, okay, you can kind of consider as v is a function of I, which is happen to be I times R, right? So function like this is known to be linear, and that's why you can apply the function first, or you can apply them separately like that, right? So this is kind of introduction to linearity. And then what superposition principle tells you is that what I can do to compute this, okay, is I can do f equal to, I can look at things one at a time, okay? I can look at this one at a time. And so, I mean, this is kind of long-winded way of saying it, but I can add them later, okay? That's basically the superposition principle. So what you notice in your circuit, these are all linear circuit, okay? Meaning that everything, all the equations you write in terms of KCL, KVL, they are linear, okay? So when we say turn off certain independent source, what you're doing is you're setting that value. So in this case, it will be I, right? So you set I to 0, means that you turn that current source to be open circuit, and then you compute the voltage at a certain node, and you do the same for the other current source, okay? All right, this is way to capture how the linearity works, and then the linearity leads to the superposition principle, okay? And then last time we talked about why it doesn't work, something like this, superposition principle doesn't work in nonlinear system, is that if you have nonlinear system, like taking more than first power, what you get is, okay, so-called cross product term. Hopefully this equation seems very familiar to you, okay? So the problem with this, if you have nonlinear system, is terms interact with each other, okay? That's defined by this cross product term. So if I did just like here, I will only get self terms, not the cross product, right? And even if you add it here, okay, this and this are not equal, right? Whereas this and this are equal, right? So that is a distinction between linear system and nonlinear systems, and that is also why you cannot use superposition principle if you have nonlinear systems. Okay, and then you have to use superposition principle to find some stuff in the assignment 3. Now, assignment 3, okay, first couple problems that are from previous final exams, right, which you can access in your library as well. And then the last of the problems are very short op-amp problems, right, and hopefully it won't take you more than 2 or 3 hours to do. Okay, now, that was so much about linear systems. And then we talked about the source transformation. Okay, so when you're solving circuits in, let's say, KVL, right, you basically have as many equations as a loop, right? But if you actually have current source with resistance in parallel, you can combine that to make that as a voltage source in series with resistor. Okay. Now that reduces the number of loops, right? So it simplifies your calculation, right? So as you do these problems in coming weeks, what you'll notice is that a lot of things you can just do based on what you learned in the first week or two. Right? There's no real reason to do source transformation. You can still solve it. Okay, a lot of problems, but it's just that the problem gets a little bit more complex, right? So, sorry, source transformation. Yeah. So it is always good to know how to use this tool so that you can cut down on your problem-solving time. And as you do, the more you learn about how you simplify the problem, that's how you start developing intuitions. Yeah. Anybody can punch numbers in and solve things at its maximum complexity, but the shorter you can make it, that means you know more about it. Okay, and what you'll also see in the final exam, okay, is that some of the problems are often structured in a way that it's solvable with kind of rudimentary methods, but it'll take like, let's say, 30 minutes. Okay, but if you know how to, or if you have good intuitions about the problem, it'll only take you 5 to 10 minutes. Okay, so there will be problems like that as well. Right, and now the final exam is 2 hours. That's fixed. Right, it's always been 2 hours. I think it'll be 2 hours till the day we die, and there are always 4 problems. Right, so it's like a 30-minute each. Right, yeah. So anyway. So that's why you don't want to just solve the problem and get the right answer. You want to think about whether there are easier ways to solve the problem. Right? I'll be smart about the problem. Okay, and then we talked about Thevenin theorem, Norton theorem. Okay, that was another way of abstracting the system into a simpler form. Okay, so I really want you to kind of think about these, concepts in certain coherent manner, right? Because otherwise, at the end of the day, you feel like, oh, I took circuit analysis, and there are like 50 things I had to memorize, right? Then you probably didn't stack your knowledge in the most efficient way. Okay, so you want to have some tree or pyramidal structures in your understanding. And the overarching theme in all this, or half of what's on this slide, is that how you view the system in a simplified manner. Okay, so we talked about how you can simplify resistive networks. That's what you did in tutorial 1. And then you also did, we also looked at the delta Y network, right? And we also talked about how you can picture some networks in an equivalent way. Or let's say, if you decide to show something in a certain way, what their constituent value should be, right? So Norton's and Thevenin's theorem are in that kind of philosophy. Right? You're trying to simplify this circuit with lots of components into a very simple system or depiction, which is, in Thevenin's case, that's a voltage source plus resistor. And then if you do source transformation to that, that's what they call Norton equivalent system, right? So they are kind of symmetric in that way. So you can find Norton first and then go to Thevenin, or the other way around. Okay. And then we briefly talked about the power, right? I think the important thing about the power is that you realize that there's no power consumption if you only have finite voltage or current, right? You need to have current and voltage together, okay? So what I mean by that is that, one kind of simple example is, you don't pay for, if you don't plug anything to the wall, you don't pay any electricity bill, right? But the plug on the wall is already supplying the voltage, right? So as soon as you put something in, it starts flowing current through whatever you shove it in, and then you pay the bill. All right. And then it's also important to remember there's a sign convention with the power, okay? Which is not surprising because we've been looking at voltage and currents in minus and plus, right? So it's not surprising the product of them, the power, will be having signs that are plus and negative, right? And then we said positive is dissipating and then negative is supplying. And if we just have a very simple circuit that has a single voltage connected to a single resistor, we can easily show that one power is, the power dissipated at the resistor is identical to the power provided by the source, right? That's another good way to kind of check your answer sometimes, because whatever power is being dissipated needs to be provided by some other elements, right? It's part of the conservation of energy, right? So after you finding all the current and voltage in your circuit, if you add up all the power and they don't net out to 0, then there's a mistake because you just broke physics. Okay, and then last thing we did was we looked at maximum power transfer, okay? And aside from just trying to memorize the equation for matching, there are 2 things I want you to know, which is that maximizing power is different from maximizing voltage or current, right? So if you want to maximize voltage, open circuit probably is the best. Maximize current, probably, you want to have a short circuit is the best, right? And the way we computed it, right, we are looking at the slope of the product, right? So it was from taking derivative and set it equal to 0 type, right? So you will see that over and over again in your remaining years in engineering curricula. So it's important that you know how the derivations are made, okay? Because a lot of times you learn about certain phenomena or you learn about certain mechanics, and then one way or not, interesting thing happen when some things are maximized or minimized, right? And if you're looking for these local maximas or minimas, then you have to take derivative and set it equal to 0 because, any curve, think about it, most of the curve will have some convex or concave form like that, all right? And so if you look at the slopes at each point, it's only 0 at the tip or at the bottom, okay? So don't just try to memorize because memory will fail you. Try to understand the nature of it or how they came from, and they will not fail you. And you will actually memorize things better if you actually understand it. So it goes both ways. And we briefly talked about the op-amp last time, but we will just do it over again because it was very brief, and op-amp are kind of a new thing that we're learning this semester. Any questions? Okay, so new things are coming in, so take a deep breath. Okay, so this is where we left at, okay? So last time we said, okay, there is this amplification element called operational amplifier, and that's a bit contrast to what you've learned so far, which is, you look at having some source with some circuit with a source and resistors and things like that. So they don't really perform any active function, so to speak, right? And the basics of electronics function is probably the amplification, and so that's why you're taught about amplifier. But now the problem is that the elements, the actual physical elements that gives you amplification is a little bit more involved than resistors. There are nonlinear elements like transistors, okay? And they are properly introduced to you through semiconductor devices, which is 2103, as well as 2102 that you take after this course, right? But before that course kicks in, we still want to give you some understanding of an amplifier, right? So that's why we introduced the concept called an operational amplifier, or rather an ideal version of it. Okay, so that's where we start, right? So again, this is also a way of abstracting, kind of difficult or complex component into a simpler form, right? So it's a little bit like, how we made a Thevenin equivalent circuit. Now here we're making ideal op-amp to depict some complex system that gives an amplification. So the basics of amplifier is you will either see so-called single-ended or single-ended or two-ended like this, okay? And the main thing is that, okay, so let's start with something obvious. Okay, this is so-called amplifier. Operational just means that it's a voltage amplifier. So it needs to amplify something, okay? It needs to amplify something, and why you'll have to amplify the input. I don't want it to amplify something random, right? So the input, okay, in this case, they're differential, all right? Differential means that it's a pair of there are two of them, okay? So what this amplifier does in this picture is that it'll look at the voltage difference between positive and negative, okay? And then it will amplify that difference in voltage, okay? And send that as the output, Vout, okay? That is kind of a simple picture of the amplifier, okay? And sometimes you will see, people may connect this to the ground, okay? So if you just connect the negative node to the ground, then, if you just apply single voltage to the positive terminal, right, it's trying to amplify the voltage difference between that VP and then 0, and then send it to the output, right? Okay, and then there are, in ideal op-amps, there are these components here, okay? There's so-called input resistance, Ri, and then there's output resistance, Rout, okay? And the gain, Vout, is actually defined as A times Vp minus Vn, okay? So what you'll often hear is that, so the way typically op-amps are introduced is that you're shown this schematic, okay? And then you're told that, okay, Ri is infinite, okay? And then R0 is a 0, okay? So whatever voltage here will be seen here, and that voltage is A times difference in Vp and Vn. So that's what you will kind of see typically, right, in textbooks. Now, it actually looks like this, right, with a lot of BJTs or MOSFETs or transistors, right? So what's inside the actual triangle may look something like that in practice, right? So this is why we don't start with that. We start with something simple, or equivalent version of this. Okay, so kind of going back to the ideal model. So these are these are the characteristics I just mentioned to you. Okay, infinite input, 0 output, infinite gain, and then these metrics kind of leads you to have 0 input current, or they're kind of going vice versa, okay? So, but instead of trying to memorize these properties, I figured maybe it's good to kind of see how they come about, okay? So let's take a step back, and then let's re-examine the amplifier a bit, all right? So let's just say we have an amplifier here. Oh, I forgot the minus sign there, sorry. But you can draw the amplifier something like that, okay? I'm connecting one node to ground, and then connecting the other to input voltage, okay? And what amplifier should do is it should give you the output with gain A, Okay, so let's not assume that A is infinite. A is some number. Okay, so that's what you get. Except I have a typo here. Yeah, anyone see that? Where's the typo? Is that typo numeric or typo sign? Numeric sign, yes. So input is going to negative terminal, so it should be the negative sign. I'll fix that later after the class. Okay, so now, this will be just kind of depiction of general amplifier, okay? But now the one thing I mentioned last lecture is there are a couple things to note. One is if gain is really high, or let's say infinity, then output is really high in infinity, and that's no fun. That has nothing to do with infinities. But practically, more important part is that we can make a high gain. We can make A high, but it's really hard to control. Okay, it's really hard to control. Like for example, we can make it somewhere between like 100, 150, but it's really hard to nail it to like 125. All right. So there is some accuracy issues in actual practical amplifier design, and then there are some other frequency-related things that we'll learn more about in the later in the semester. Okay. So using an amplifier like this, as is, okay, they say it's open loop. Okay, is not always desirable. Okay, so instead, what we do is we employ a type of technique called feedback, okay, that can make the whole system, meaning that amplifier plus the feedback, more usable or practical. So what do I mean? Okay, so we'll do a quick, very basic introduction to signal and systems here. So this is something you'll learn more about 2110. Maybe some of you are taking, I don't know. Don't worry, we're not really going in any depth here, okay? All I wanted to say was, again with the typo here, if you have an amplifier like this, or any element that amplifies your signal, or any element that does anything, in signal and systems, what you can do is you can draw it like this. You can draw it as box, okay? So we can replace the box as A. So this is a little bit like block diagram we talked about in the first lecture, right? So you see how the themes are still overlapping here. And so let's say you have some box. Doesn't have to be an op-amp, any box, okay? That gives you V out that is A times V in. Okay. Now we said that controlling A is very difficult, and there are other issues, so we want to have a feedback. And in this signal and systems view, what the feedback can be drawn is, okay, instead of just having going straight from V in to V out, we'll take a little bit of V out and feed it back to V in. That's why it's called feedback, right? And if we keep adding stuff, right, that will be stable or unstable. Let's say A is positive. Let's say normally A increase the V in to V out, right? And then let's say, I said, okay, I'm going to stabilize this, and then I'm going to have a feedback which samples the output or takes the output and add positively to the input. Does that sound stable to you or unstable to you? Unstable, yes. So, the rationale is that you can kind of, if it's hard to see, what you can do is you just put some numbers in, okay? So let's say, okay, V in here is 1, okay? A is 10, all right? So normally V out is 10, okay? But let's say I take 10 and feed back here and add. Okay, then what I'm going to have is now 11 at the input, right? Now 11 gets multiplied by 10, so it becomes 110, so on and so on. So it continuously increases, right? So positive feedback is inherently unstable. So when we do these type of discussion, we always talk about negative feedback, okay? And I think you've probably seen that in one of the quiz questions. Is